Hey everyone, so we're going to work through the second part of the practice exam 2 here. Plus we'll do question number 8 here. That wasn't on the first video. So question number 8 is a true or false. And the statement is, it is possible for accounting and economic costs to be equal, but it is never possible for economic costs to be less than accounting costs. All right, so let's look at the definition here. What are economic costs? It's accounting costs plus opportunity costs. Now, opportunity costs could be zero. In that case, economic costs and accounting costs are equal to each other, which is what the first part of this says. But it says it's never possible for economic costs here to be less than accounting costs. Since these opportunity costs can never be negative, well, by definition, we know this statement is true here, right? And economic costs are either greater than or equal to accounting costs here. Okay, so that's true. All right, so let's move on to what the main thing we're going to do here. Let's go over part 2 of the practice exam. All right, so let's pull this up. Okay, so the first thing we're looking at is indifference curves. And so Erica enjoys company of her cats and dogs. However, there must be 3 dogs for every cat that she owns. Her utility can be described as U equals the minimum of D 3C. So these are complements. She likes these ratios together here. All right. She enjoys having 1 cat for every 3 dogs that she has. If this ratio gets out of whack, well, it doesn't provide any more utility. Okay. So let's talk about this. So here's cat choice. Here's the dog choice. So essentially, let's say the utility is 3. All right. So that's the minimum of what? Well, dogs is just equal to the variable here. So it's going to be 3 dogs. Cats, remember it's 3 times the quantity of cats. So that's just 1 here. Okay. So 1 cat, 1, 2, 3 dogs. All right, this is where the kink set on this. Now let's talk about the rest of this indifference curve. If she increases the number of cats, well, this is still going to be on the same indifference curve because the utility is just a minimum of these. You increase the number of cats, well, the minimum here is 3, so it's going to give you the same thing. All right, she likes having this ratio of cats and dogs together, right, the way they play together for whatever reason. And if she increases the number of dogs and still only keeps 1 cat, well, it's going to stay on this indifference curve as well too, right? Having more dogs and she only has 1 cat, it's not going to bring any more utility for her. She doesn't like this. She likes the ratio of three dogs for every cat. So this is this indifference curve here where the utility is 3. Of course, you could go to 6. Essentially, what you would do here, you would need to increase the number of dogs to 6, the number of cats to 2, and this will give you your kink for this. Okay, and this works the same way. If you increase the cats past 2 with only 6 dogs, well, the utility is not changing. The same if you keep cats at 2 and increase dogs from 6 to 7, 8, 9, and so on. Your utility is not increasing. She likes to keep the same ratio. Okay. So the next part here, it's asking how much utility will she get from 30 cats and 7 dogs? Well, let's plug this into the utility function here. Minimum 7 dogs. So remember, that's just D, so that's 7. Cats is 3 times the number of cats. The number of cats is 30. Okay. So what's the minimum of these numbers? The minimum of 7 and 90 is 7. So the utility here is going to be equal to 7. Okay. She has all these extra cats. They're not really bringing her any more utility because she doesn't have enough dogs to go with, the way that, the cats are dominating. She doesn't like the way they act and they have too much power or whatever. But, so utility she's only getting here is from this, is a 7 here. Okay. All right. So that's the example of an indifference curve. The next thing we're doing here, we're looking at a few questions looking at costs. Here we're looking at two questions that have to do like with, when's your average variable cost, minimizing. So this first one here is giving you these two functions. One's the total cost and one's the marginal cost. So we'll start off with the first part of number 9. Let's erase this first. All right, so we have total cost equals Q3 minus 50Q2 plus 800Q plus 100. Marginal cost equals 3Q squared minus 100Q plus 800. Okay. Now, it wants to define expression for the firm's fixed cost. What is this? This is when you have a change. Sorry, no change. This is when you have what is your cost going to be regardless of what you produce here. Okay. So it doesn't matter what you produce, these costs are set here, they're fixed. So this right here would be this 100 here. This is the fixed cost. You think this maybe is rent or something like that. So it doesn't matter what you produce here, you're paying this $100 a month. Q could be 0, you're paying 100. Q could be 2, you're still paying this $100 over here. It's not being affected by quantity of production here. Okay. Now, variable cost. What is this? Well, this is everything else here. Variable cost is Q3 minus 50Q squared plus 800Q. All right, this is our formula here for variable cost. As you can see, it's going to change based off, the amount of production that takes place. Average total cost. We just take this whole expression, Q3 minus 50Q squared plus 800Q plus 100, and we just divide that by Q. What does that give us? Q squared minus 50Q plus 800 plus 100 over Q. This is our expression for average total cost. Expression for average variable cost. We do this similar, except we leave out the fixed cost now. So it's Q3 minus 50Q squared plus 800Q divided by Q. And so our average variable cost is going to be Q squared minus 50Q plus 800. Now, these two terms are going to have relevance. When we get to this next chapter, you'll see why they're really important. But one thing it has to do here, and we'll go ahead and show this, is like, what output here is going to minimize, your average variable cost. Okay. That's what we're going to do here next. Now, this up here. All right. So we want to minimize this. When is the average variable cost minimized? Well, it's when it's equal to the marginal cost, because the marginal cost is going to be increasing. And then as long as the marginal cost is lower than the average variable cost, well, it's going to pull this average variable cost down. But as this marginal cost keeps going higher and higher, at a certain point, it's going to, be equal to. Then at that point on, it's going to pull up the average variable cost. It's going to start increase instead of going down. Right? So we know the point where these two meet each other, equal each other. That's where the average variable cost is minimized. Part B here. Find the output that minimizes average variable costs. So we'll set marginal cost equal to average variable cost. And so what do we have here? Marginal cost we said was we said was 3q squared minus 100q plus 800. And what is average variable cost? Well, that's q squared minus 50q plus 800. All right, so, well, these 800s will cancel out. Okay. What else can we do here? Well, we can subtract q squared from both sides. That eliminates this. That brings this to 2q squared minus 100q equals negative 50q. What can we do now? Well, we'll add 100q to both sides. All right, what does that do? Well, that eliminates it from this side. That leaves it with 2q squared equals 100q minus 50q. So you'd have 50q on this side. So these will cancel out. You're left with 2q equals 50. Divide by 2. You're left with q equals 25. So that's the quantity that minimizes your average variable cost. Okay, production level of 25. Okay, so that's it for the first part. The next one, kind of look at these similar. Here we're just looking at the long run total cost and your long run marginal cost. Okay, this is what the firm will look at, like when it's trying, to see, when it's facing economies of scale. That is, if it increases production, will it see lower cost along the way, or will it face diseconomies of scale? At that point, that's when it's if the increase in production past that in the long run, you'll see an increase in its cost along the way. This average total cost. All right, so let's write down these long run total cost function we have here. Is 20,000 q minus 500 q squared plus q to the third. Now here are these long run total costs. This is when you can adjust. You can adjust your level of capital. Anything, there's no constraint here about what you can adjust. You can choose any ratio, capital and labor. There's nothing holding you back with that. Here's our long run marginal cost. 20,000 minus 1,000 q plus 3q squared. All right, so this is similar here. Like you're looking at, looking at things in the long run where you can, either add capital or labor. There's no constraint. So what is the marginal cost here? When you can do that, you're not just kind of set with a fixed level of capital as we usually think about it. All right, here, like you could adjust either one, capital or labor. So at what levels of output will the firm face economies of scale? So what we do here is we need to set these two together to find the minimum point. Right? Part A, set long run marginal cost equal to long run, the average long run total cost. And so when you do that, let's see, sorry. That's going to be 20,000 minus 1,000 q plus 3q squared equals the average long run total cost. So that's going to be 20,000 minus 500q plus q squared. Okay, so get the average long run total cost. You're just you're just taking this long run total cost and dividing it by q. Okay, that's where we're getting that from. Okay, so what can you do? Well, first, you can get rid of the 20,000. All right, what about anything else here? What can you do? Well, you can subtract q squared from both sides. That'll eliminate this. And this will go to 2q squared. Right. This goes to 2q squared. We still have this negative 1,000q. And this is equal to negative 500q. So what can we do here now? Well, we can also add 1,000q to both sides. It eliminates that. This will give you 500q on this side. 1,000q minus 500q is 500. So 200q squared. Divide both sides by q, we'll get 2q equals 500. And so if you divide both of those by 2, Q equals 250 is what you'll get here. So that's the point that minimizes the average, long run total cost here. So where does the economy face economies of scale? Well, that's when the quantity is equal to 0 through 250. This is when it experiences economies of scale. The next part asks, well, when does it experience diseconomies of scale? Well, from this point onward, this marginal cost is going to be higher than the average long run total cost. So it's going to pull the average long run total cost up. So here the company's facing diseconomies of scale. So that's when quantity is equal to 250 through infinity. Right? And also it wants us to, it asks us, does it experience this typical U-shaped shirt? Typical U-shape? Well, yes, it does. So let's just draw this out, what it looks like here. All right. So here's our various costs, whether it's marginal or long run total cost. Here's our quantity. All right. So we'll say our marginal cost. So we'll start here, do something like this. What about our long run average total cost? Well, it's going to look something like this. Done like this. I'm going to connect. And then from that point forward, it's going to increase. Okay. Here's where it's minimized at, and that's 250. So from here, shoot, I wrote a D. It's experiencing economies of scale. Let's just write it out. So what's going on here for the company? Well, as it's getting larger, it could take advantage of a specialization more, specialization in labor that it hires as it gets bigger, also specialization in the equipment that it uses. This gives it an advantage as it gets larger, it gets lower costs. Another thing that goes on here too is like, as the company gets larger, it's going to get better deals on raw materials as well too. This really isn't included in our function more than likely, but that's part of it too that goes on with this. All right. Then it gets here where it's constant. There's like no change. All right, if you increase or decrease right here, it's 0 is bottom out. It could be the case. Now we're just saying it does this and starts back immediately. It could be the case where it looks like this. It's flat. All right, so the company could choose to pick production anywhere from this point. Let's say this is 100 to 300. All right, and that will be minimizing its total cost. So that's probably where the company would want to try to produce at. Okay, whatever here would maximize its profits. That's probably where it's going to be, because this is lowering its average, total cost of production for each good that it produces. Okay. But here, the way this one's set up is like it's immediately going to start going back up. All right. And then once it starts going back up, you have these diseconomies of scale. And that means as a firm producing more goods, well, its costs are going up on average, which is not good. It doesn't want to do. It wants to avoid that. Now, maybe the case where it needs to go a little past that because the way it's set up, like with this amount of capital that it has. But like in the long run, you want to adjust that. You want to try to make sure you're on this other side here. As long as you can sell your good, you're going to keep increasing. But once it gets to the point where it starts average costs start going up, the average total cost, well, you probably don't want to keep increasing the amount of good that you sell at that point. Okay. All right, so that's it for this question. All right. Next question here. All right, here we're looking at a problem with producer optimization. All right, so we're given a given the firm's production function. This is Frank Bean. He makes hard cider. And his production function can be shown as quantity equals 5 times K to the 2/5 times L to the 3/5. All right. And so the marginal product of labor is, 3 K to the 2/5 L to the negative 2/5. Marginal product of capital, 2 to the K to the negative 3/5 L to the 3/5. So what are these looking at? Well, this is showing, like, based on how much capital labor you're currently at, what happens if you increase by a unit of capital? What happens if you increase by a unit of labor? Marginal product of labor, of course, is looking at just changing the labor. Marginal product capital is looking at just, incremental increase in capital. What happens to your production when that happens? So it's basically showing, how productive you are, all right, with using either capital or labor. All right, so let's look at another thing that's important here for Frank Bean is the cost of capital and the cost of labor. So the rental rate, this is the cost of using capital, is $12. What about labor? Well, that's just the wage rate. That's the price of labor. That's just $18 per unit. Okay. All right. What do we want to do here? We're going to say, okay, he needs to produce 500 bottles of cider a day. Okay, so what's the cost saving amount of labor and capital? Here we're assuming that he can adjust his capital and labor to whatever gives him, the lowest cost here. So the first step here is we want to find marginal rate of technical substitution. All right, and so what is this? Well, that's just the marginal product of labor over the marginal product of capital. What's the marginal product of labor? It's 3K to the 2/5 L to the negative 2/5. Or the marginal product of capital, that's just 2K to the negative 3/5 over L to the 3/5. Okay, so what does this do? This gives us 3/2 capital. Right. Well, we have this 2/5 units up top and a negative 3/5 on the bottom. So what we need to do is just, we need to switch, take this K to the negative 3/5, rewrite it as K to the 3/5 if we put it on top here. So we'd have K to the 2/5. If we rewrite this on top, we'll just switch the sign of the exponent. It goes to K to the 3/5. What about here on the bottom? Well, we have this L to the 3/5. Well, let's bring this L to the negative 2/5 on the bottom and rewrite it. And it's just L to the 2/5. And this going along with L to the 3/5. We can get our answer from it. So this is 3/2. K to the 2/5 times K to the 3/5. It's just K raised to the 2/5 plus 3/5. This is just 1. So we got K here on top. What about on the bottom? L to the 2/5 times L to the 3/5. That's just L raised to the 2/5 plus 3/5, which is just 1. So we have L here on the bottom. Okay. So 3/2 KL, that's our marginal rate of technical substitution. Now we want to set marginal rate of technical substitution equal to the slope of the ISO cost line. And that's just the wage rate over the rental rate here. Okay. So what's that going to be? That's going to be 3/2 KL equals to the wage rate, which is 18, over the rental rate, which is 12. Let's cancel out. What does this give us? Right. If we multiply both sides by 2/3, that's going to give us 36/36. Oh, there you go. I didn't write this good. Let me just do this right here. All right. So let's multiply both sides by 3/2. This eliminates it on this side. So we have K over L equals, it needs to be 2/3. Daggone. Two-thirds times 3/2 is 1, so that eliminates it out. What about this other side? Well, that's going to be 36 over 36. That's just one. So essentially what's going on here, the capital and labor that's used is going to be the same. You're going to use the same amount. You know? Right. Why is this? Like, well, if you look at how productive they are, you know, the labor is a little bit more productive, but the labor is a little bit more expensive though. And so because of that, they kind of cancel out, and like you're going to use the same amount of each. Once you take into account that, you know, the labor is a little bit more productive, but it costs a little bit more. You know, and at the end of the day, that's what you're trying to do is minimize costs. In order to do that, you're going to like keep this constant ratio of capital and labor. All right. So now what we're going to do, we're going to substitute this into the constraint. And our constraint is that he needs to produce 500 units of cider here. Okay, he needs to produce 500 units. Well, what's his production function? Well, it's 5K to the 2/5 L to the 3/5. All right. So we want to substitute K equals L. We know this is a ratio we need to use. We know we need to produce 500. And this will tell us how much we need to employ both of these to be able to produce this much. Okay, so 500 equals 5. Let's substitute L here. L to the 2/5, L to the 3/5. So what does this equal? 5 times L equals 500. Divide both sides by 5. So our optimal amount of labor will be 100. And guess what? Since capital is going to equal the labor here, so it's going to be 100 as well. Okay. So we're going to use 100 units of labor, and he's going to use 100 units of capital. That's going to, minimize this cost here. All right, what do we do next with this problem? Okay. Well, it wants us to draw a diagram of the isocost line, the isoquant curves, with the cost minimization combination plotted. All right. So capital here we'll have on our y-axis, labor on our x-axis, and we're going to use 100 of each. That's what minimizes this cost here. Here's our isoquant. Any combination on here will give us a production of 500. Okay. But what we're going to do, we want to minimize these costs. And so this ratio right here will minimize this level of cost. Let's solve for the cost. We said that the wage rate was $18. We're using 100 units of labor. We said the rental rate was 12. We're using 100 units of capital. So what does this give us? 1,800 plus 1,200. Our cost equal 3,000. All right. So your cost there are going to be $3,000. Okay, so that's our there we're plotting it out. Remember what we did here. He knows he's got to produce 500, so he's got to use some combination right here. All right. What you can do is set the margin rate of technical substitution equal to the isocost. This will give you this point right here. And so what you do is you substitute that into here, and this will give you what combination where these two are tangent right here. And that's what minimizes your cost. All right, now what happens is this next part that we got to solve for. A new yeast is discovered, I spelled discovered wrong, that shortens the fermentation time, which means it's more productive. He can produce more with the same amount of capital and labor. As a result, his production function changes to Q equals 7Q 2 to the 5th over L to the 3/5. All right. So what happens to the new cost minimizing units of capital and labor here? We'll see what happens here. All right, essentially what happens, do I want to go through all this or just I'll just go through all of it. Do a shortcut. First, find the marginal rate of technical substitution, marginal product of labor, or marginal product of capital. What is this? Marginal product of labor is, no, I didn't do it that way on this. I just put it, the fact that it's 7/5 more efficiently. So it's going to take, 5/7 as much of the input here. All right, because instead of going through all that, let me just show you the shortcut here. Essentially, capital labor is just as productive. The costs are the same here. Our new production function is Q equals 7 K to the 2/5 L to the 3/5. What was the old one? Well, that was Q equals 5 K to the 2/5 L to the 3/5. Okay. All right. So essentially, now it's 7/5 more efficient. Production is. So you put the same amount of capital and labor in there before, it's going to give you 7/5 more. All right. So you need to use 5/7 of the level of inputs before as you previously did. Okay. So what's the new labor? Well, you use 5/7 as much. 5/7 times 100 is 71.42. Remember, that's going to be our level of capital as well here. The price of these hadn't changed. How productive they are hadn't changed. One of the things changed is that they're both more productive now because of the shorter fermentation time. All right. So the new amount of capital and labor that we use is 71.42 instead of 100. So we can draw this out. K over L. Remember, our old one was here. Our cost was 3,000. You had to use 100 of each. That's our old 500. But now you only need to use 71.4 of each one of these. That's our Q of new equals 500. And this cost, what is this going to give you for cost? Let's calculate that. Our new cost is essentially going to be 5/7 of what we had before. We can go ahead and just put these in now. The wages are $18 times 71.42 plus $12 times 71.42. What's this going to give you? 30 times 71.42. $2,142.60. That's our new cost here. You see, you're saving a good bit of money. That's because he's more productive now due to this fermentation. This is what increases production. Increases the standard load. It's these different types of things that we come up with, these new technologies that that causes our labor and capital to be more productive here. That's how the standard of living increases for everyone. That's what's happening here. Shortens fermentation time. He can produce more cider. Well, as a result, his production increases, and he can produce the same amount with less units of capital and labor, and as a result, his costs have gone down, and he has more profit as a result of that. Okay. All right. So that's it for that problem. Let's go to the next one. What's our next problem? Here we have a problem with perfect substitutes. And this is looking at perfect substitutes with a sushi bar called Mishima's. So Yukio has this, like he makes use of robots now. And they can perform the job of 2 workers here. Okay. So these robots and workers are essentially, perfect substitutes for one another. Right. What is his production function? Q equals 6K plus 3L. So essentially what's going on here is the robots are twice as productive as the workers are in this case. That's what's going on. How much does the robots cost? The rental rate here is $20 per unit, whereas for the workers, their wage is $15. Okay, so let's say he wants to serve 200 dishes of sushi a day. What combination of capital and labor should he use to minimize costs? So what we'll do here, we'll use this bang for buck method. All right. So essentially the bang for buck, you know where you're maximizing. The ratio is going to be MPL over MPK equals the wage rate over the rental rate. So we can rewrite this though and use the bang for buck method. MPL, marginal product of labor divided by wage. This is giving you, well, how much production can you get out of additional unit dollar here spent on labor here? And we'll compare this versus marginal product of capital divided by the rental rate. All right, for each dollar, you know, how much more productivity can you get from purchasing another unit of capital here? And so what are these? The marginal product of labor here is 3. The wage rate we said was 15 versus the marginal product of capital. Well, that's just 6. You divide by R. The rental rate, that's $20. So it's essentially just 1/5 versus, let's see, how does that simplify down to? What's the common thing here we can shorten this to? Divide that by 4. So that's 1.5 over 5. So as you can see, the capital here is more productive. Okay. 6 over 20 is greater than 3 over 15. All right. That's the capital is not more productive. Capital per unit is cheaper to, increase your production using capital than labor here. More bang per buck with capital. With taking into consideration the capital, the robots here are twice as productive, but they do cost a little bit more, but it's not twice as much. So you should employ nothing but capital here. Okay. How much do you need to produce? It needs to be 200. You're going to use nothing but capital, right? How much capital do you need to use to do this? You just divide both sides by 6. This will give you your level of capital. 200 divided by 6 equals 33.33. Okay. All right. So that's how much capital he needs to do to produce, 200 dishes of sushi a day. All right. So he needs to make sure he has enough robots that they can provide 33.33, hours of work here for him, basically. So now we want to draw an illustration. I'm showing his isocost line, isoquant curve. And we want to make sure we plot the optimal combination as well here when we do this. All right, so we have our capital on the y-axis. On the x-axis, we have our labor. We know what maximizes our production here. This is 33.33 units of capital. This is our optimal combination here. All right, so how much, let's do the isoquant here. How much labor would we need to employ to produce the same amount? Well, we know it's going to take twice as much because these robots are twice as productive here. So it would take 66.67 labor here. Produce 200 dishes each day. And what about the ISO cost line? Well, we know it's going to be steeper here. Because we know for the same cost for capital, we can't employ as much labor here. That's why we're choosing this. Okay. Remember, so, if we choose this, well, this is what let's just say it's 150. Okay. We know we're not taking this out as far as we can here. We're not minimizing our cost. Okay. Here we're minimizing our cost. We're getting this where, we the level of cost here is like, lower than what it would be otherwise. So let's say if we spend all our money on 66 units of labor, well, the ISO cost line would be something like this. I did it the wrong way there, sorry. Well, this is more expensive here than what we've got here. Okay. C2 is greater than C1. We're not minimizing our costs. We want to go as far down as we can with this until we just can produce just enough here. All right. Here on this ISO point line, we can produce 200. This is what's minimizing our cost here. Okay. So we want to employ nothing but capital in this case. All right, we're going to look at this next part here. It's saying what happens if there's a chip shortage. This drives up the cost of using these robots here. They're more expensive to work on, to fix, to buy. The rental rate is going to increase as a result of this. It goes up to $40. Okay, so now this will change our bang for the buck thing. Now we're going to compare these now. Marginal product capital, the price of capital, this is the rental rate. Now we're going to compare this to the marginal product of labor divided by the wage rate. That's just our price of labor. We have there. Marginal product of capital is 6. Our cost now is 40 though. Well, the marginal product of labor stay the same. It's just going to be 3 over 15. Right? Well, now this is more than that. Okay. So if you do the math, 315 is higher than 6 over 40. All right, because this is the same as like 3 over 20. So obviously this one's higher now. So now you get more bang for your buck by using labor. So you want to use nothing but labor now. So let's stick this in our production function. We want to produce 200 dishes. We want to use nothing but labor. So you get, for every unit of labor, you get 3 dishes. So what's this going to give us? We divide by 3. 200 divided by 3 equals L squared. So it's going to be 66.67 units of labor. All right. So yeah, our robots they're more productive. They're twice as productive as humans, but now the cost is more than twice as much as it is to employ, just labor here. So you're going to choose now to just use labor here. Okay. So it's not just how productive they are, it's also the cost here. That's what the firms are looking at here. They're looking at productivity for capital labor and also the cost. And that'll guide them like which one's the best choice to minimize their costs. All right, so shoot. All right, so our last problem here will be a consumer optimization problem. All right, so Deborah really enjoys kayaking and hiking at national parks. Hiking trips cost them $800, kayaking $900. Assume that Deborah has $4,500 of income to spend each year. Additionally, her utility function can be represented by U equals 2H to the third, K to the 2/3. So here's our utility function. And our marginal utility for hiking trips, and our marginal utility for kayaking can be represented by marginal utility of hiking, 2/3 H to the negative 2/3, K to the 2/3. Marginal utility of capital is 4/3 H to the 1/3, K to the negative 1/3. All right. Additionally, we want to know the price of these two. We said that was price of the hiking was $800. Price of the kayaking was $900 per trip. Okay, and we said she had an income of $4,500. Now, what is the optimal number of hiking and kayaking trips for each year? Well, first we want to find marginal rate of substitution, which is just the marginal utility of hiking over the marginal utility of kayaking. So this is 2/3 H to the negative 2/3, K to the 2/3 over 4/3 H to the 1/3, K to the negative 1/3. Okay. How can we rewrite this? Well, these threes will cancel out. Then we'd have 2/4, which is the same as 1/2. All right, now what about the rest of this? Remember that H to the negative 2/3 is the same as 1H to the 2/3. So we can write that on the bottom now. H to the 2/3. That'll go along with H to the 1/3. What about this K to the negative 1/3 here on the bottom? Well, 1/K to the negative 1/3 is the same as K to the 1/3. So we can rewrite this on top. K to the 1/3 times K to the 2/3 here. All right. And K to the 1/3 times K to the 2/3 is just K. So we have 1/2 K. H to the 2/3 times H to the 1/3 is just H. So marginal rate of substitution is 1/2 K over H. Okay. All right. Now we want to set this equal to the slope of the budget constraint. What's the slope of the budget constraint? That's just the price of hiking over the price of kayaking. So 1/2 K to the H. Price of hiking, which is $800, divided by the price of kayaking, which is $900. So this is essentially going to give you K to the H. When you multiply both sides by 2, that eliminates it on this side, and that gives you 1,600 over 900. Okay. And so that can simplify down to essentially 16 over 9. And so if we multiply both sides by H, our ratio is kayaking 16 over 9 hiking. Okay. So whatever amount of hiking that you do, you want to do that times 16 over 9 for kayaking. Okay. So you're going to do more kayaking than hiking essentially here. Now you know this ratio, but you don't know. Okay. Now this is where you got to bring your constraint in. What are you constrained by? Well, you're constrained by your income and the price of each of these. That's what you got to take into account. All right. You're going to spend every bit of your $4,500 income, and you're going to spend it based off of the price of, the price of these two goods here, the hiking and the kayaking. So let's erase this. Substitute into budget constraint. Our budget constraint, remember, is income times the price of hiking times the number of quantity of hiking plus the price of kayaking times the quantity of kayaking. Our income was 4,500. Price of hiking was 800. Right. times H plus the price of kayaking, we said was 900 times the quantity of kayaking. So we want to substitute this right into here. What do we have now? 800 times hiking plus 900 times 16 over 9 hiking equals 4,500. All right, what does this give us? This gives us 800H plus 1,600H equals 4,500. So we divide both sides by $2,400 here. We'll get the optimal number of hiking here. $4,500 divided by 2,400. And so that's going to give us 1.875. Okay. What about our quantity of kayaking? Remember, the ratio we said was 16:9. This number of hiking, 16 over 9 times 1.875. That's going to give us 3.33. Okay. So the optimal number of hiking trips is 1.875. Optimal number of kayaking is 3.33. The way you can think about, since they're not even numbers, is, maybe some years you hike once, you kayak 4 times, maybe sometimes you hike twice and only kayak 3 times, something like that. But over the years, and this is what it's going to average out to. This is your, your level of income, and this is the price form. All right, what's our next part? How much utility does this bring? Well, we just substitute these numbers into our utility function. Utility equals 2 times 1.875 hiking raised to the 1/3, and 3.33 raised to the 2/3 with the kayaking. That gives us a utility of 5.5. Now we want to draw the budget constraint and indifference curve and plot the optimal bundle. Kayaking here on the y-axis, hiking here on the x-axis. All right. So with the amount of income she has, the most kayaking she do would be 5. The most hiking she could do would be 5.65. This is the budget constraint. And so what's the optimal bundle here? Well, it's 3.33 with kayaking and 1.875 with a hiking here. And so her indifference curve would look something like that. There's the optimal bundle right there. Okay, so lastly, there's one more part here. What happens if the price of kayaking falls to $600? So we need to redo this now. We have to redo all these steps. Now our marginal rate of substitution hasn't changed. It's still 1/2 over KH. But now the slope's changed. Okay. Instead of $900, it's $600 for kayaking. So it's going to be $800 over 600. So now if we multiply both sides by 2, we'll get K over H equals 1,600 over 600. All right. So that's going to give us something like 8/3. All right. And so if we multiply both sides by H, we'll get our ratio here. For each kayaking trip, it's going to be 8 over 3 times as many hiking trips. Okay. This is our ratio, our new ratio here that we got to use. So now we got to substitute this into our budget constraint, which we said was 4,500 for income times the price of hiking times the quantity of hiking plus the new price of kayaking times the quantity of kayaking. So we'll substitute this into here. 800H plus 600 times 8/3 over H. And what does that give us? That's still going to be 1600 H, 800 H, 4500. So this is going to essentially give us the same thing for hiking, 1.875. What's going to change though is the kayaking. All right, because our kayaking now is 8/3 times 8. So what does this give us now? This gives us 8/3 times 1.875. So the new quantity of kayaking is going to be equal to 5. Right. So now we'll go on 5 kayaking trips and 1.875 hiking trips. Okay. All right. So that's it, I believe, for this. Hope this was helpful to you. Stop the share there. And that's it for this. All right. Bye.